Hello there, General Kenobi. I'm sorry, I just had to say it. Uh, okay, today we are going to be learning about the basics of kinematics. Okay, and today's lesson is going to be a very interesting one in the fact that I'm going to be telling you a lot of stories to help ease your understanding of the topic. So sit tight and listen. All right. So before we begin, I'd just like to ask you something. What do you think kinematics means? It's such a long word, right? Kinematics, and we find these long words everywhere. Whenever we study science, we find such long words. All right. So kinematics, if you see the first four letters, kine, it comes from a Greek word, kinesis. All right, and kinesis means movement. So kinematics, if you just stay with me a bit here, movement translates to motion, right? So what do you think kinematics is? It's a study of motion, right? Study of motion, simple as that. Okay, matics refers to study, mathematics, uh, mathematics refers to study of math. So it's basically like that. Okay, so kinematics is the study of movement or the study of motion. So in this lecture today, we're going to be learning about motion. Okay, let's begin with the definitions. Definitions, all right. Now, most of us, particularly in India, what we think is that physics is all about numericals, right? Solving as many numericals as you can. The tougher the numericals you can solve, the sort of the more intelligent you are, the more you get to brag about it to your friends, and you get a lot of attention from the teachers. But that's not what physics is about. Physics is about some basic concepts, and the theory. I feel the theory is more important in physics than the numericals because the theory is what gets you through, right? If you have practiced a numerical 100 times, you will be able to reproduce it in whatever scenario possible. But if you have a definition correct, then you don't need to practice that numerical 100 times. You follow that definition, you follow that concept, and you get the numerical correct when you look at it the first time because you know how to approach that problem. All right, so let's begin with the definitions. And the first thing, the first sort of parameter I want to define here is displacement. Displacement. Okay, displacement. And we define displacement as the shortest path, in brackets, straight line. The shortest straight line path, alright, between 2 points. So, in accordance with this definition, what do you think should be the displacement between, if say a body moves from A to B, what should be its displacement? It should be the length of this line. The length of this line between A and B is the displacement. Alright. And we usually denote it by X or S as per the convention. We can use either one of them. And now I'll be defining distance as a sort of comparison and contrast with displacement. We'll be defining distance, right? And now distance is very intuitive. Uh, every time you take a ride in your car, you get to know what is the distance you've traveled, right? You just look at the distance indicator on the driver's side and you see the distance you've traveled, the trip, the trip distance from your destination to the beginning of, from the beginning of your journey to the destination, right? So distance is basically the total length of the path traveled. Right? Very simple, and it's also very intuitive. We've been learning about displacement since about distance since we were children, basically. And suppose I have the same 2 points A and B, but this time you're going there in a car. All right. So first you have to get out of your house into the lane, and then you get onto the main road or the bypass route or whatever. Then you get onto a bridge or a flyover that takes you like this. Then there's a sort of zigzag route where you have to cross many lanes and maybe some residential complexes before you finally reach the destination B, which might be maybe a shopping mall or some sort of theme park, maybe, or something like that. So, this total length of the path from A through the lane, through the main road, through over the bridge or flyover, through the small lanes and the zigzag routes to the final destination B. This is called the distance, the total distance traveled. Alright, and distance is also depicted as x or s, but that's not really a very important topic. Okay, now I promised you stories when I began this lesson, so let's get on to that. Story number 1. Alright, now let's say you are a pirate. A pirate. This is 1500s, 1600s, somewhere around that time, and this is your ship, your brig. Let's say it has a figurehead of a unicorn on its stern, a figurehead of a unicorn on its stern, and this is the bow of the ship. And let's make a few masts as well. This is the main mast with a sail. This is a main mast with a sail on the mast. Okay, and you're flying your pirate colors also up there. And this is you, the captain of the ship, and you are holding the wheel of the ship in your hand. All right. This is your trusty brig. This is SS SS Pirate, let's say. Okay, and you have spied through your spyglass. You see an X mark on a nearby island, and what does the X signify? It's treasure, right? And you being a pirate, you need to get that treasure. Okay, so how do you get to the treasure? Okay, let's say if the wind favors you, you go straight towards the island, straight towards the X mark, right? You go straight in this direction. Okay, so what do you think? What do you think this distance, the straight line distance from wherever your ship, whatever the coordinates of your ship to the coordinates of the X mark on the island, what do you think this will be called? According to our previous discussion, this is the shortest straight line path, right? You're going straight from point A, where your ship is, to point B, where the island is, right? So this is going to be the displacement. Am I right? This is going to be the displacement. That's simple. Now suppose there's another small boat here, a small boat, and it's got pirates below deck. I know small boat doesn't have a deck as such, but let's just say there's pirates below deck, and you being a pirate, being ambitious, you need to take out your rivals, right? So what you do is you first go to that boat, you get rid of the other pirates so that they can't lay claim to the treasure, and then you go to the island, right? And then you go to the island from there. So what do you think this distance will be called? What do you think this the length of this path? Let me do something. Length of this path plus this path, and let me just name these locations, these coordinates, as this point is A, this as B, and this as C. Okay, so what will be the distance from A to B? What will we call that? I'm sure you must be thinking we'll call that distance, but no, this is also displacement, right? It's a displacement from A to B. It's a displacement from A to B. Okay, and what do you think this distance from B to C will be called? Yes, you guessed it right. It's again the displacement from B to C. Okay, displacement from B to C. Okay, now you must be thinking, hang on a minute, this is all about displacement, right? And I'll also add something else. Displacement from A to C. The initial one is displacement from A to C, or from ship to treasure. All right. Okay, so now you must be thinking, this is all about the displacement, right? Where does distance figure into this? Where does distance figure into this? Now let's say the beginning of our journey, our initial point is at A, and the final destination is the X mark on the island, which is at C. All right. So what will be the distance? It's the total path length. I have first taken the path to B to take out the other pirates in their boat, and then I've taken the path from the boat to C to get at the treasure, right? So distance in this case, let's take a different color. Yes, this is all right. Distance in this case, distance from distance of actual paths traveled, actual paths traveled in this case is AB. Let's say the displacement from A to B is called AB plus BC. Isn't that right? Displacement from B to C, we call it BC. All right. So the distance is the total path that we have actually traveled. We have actually traveled from A to B, then from B to C, right? So the distance of the actual path traveled will be AB plus BC, and we call this as the distance. Okay, I'm just underlining the first word. We call this as the distance. This is not the displacement. It is a sum of two displacements in this case, and in a similar way, we can, let's suppose there's a curved path like this. All right, let's say there's a curved path like this. This is a pretty advanced analogy here, but it's all right. It's all right. It's a curved path. So distance is this total thing, right? This total thing is the distance. So what do you think? How can we talk about the distance in terms of sum of the displacements? We can make very, if I actually try to zoom in, let's say I have a microscope right here, and I've zoomed into that. Okay, and I make a zoom in sort of symbol, a circle to symbolize that, and you see this path which appears curvilinear at first glance. See, it's a very small displacement, then another very small displacement, then another very small displacement, then another very small displacement, then another. The shape is going wrong, but let's say it's like this: a very small displacement, a very small displacement, a very small displacement, a very small displacement. All right. So you see, it's a sum of displacements one after the other, right? And basically that's the whole point of the matter. The distance, the total distance what we speak about here, it's a sum of many small displacements from the initial point at the beginning of our journey to the final point, which is our actual destination. And what I have shown here, it's just two displacements because it's a highly simplified version. In reality, even if you had a real ship, a real pirate ship, the wind would be taking you, right? The wind on your sails would be the actual driving force behind reaching there. So the wind would not take you straight, it would also take you through a sort of curved paths along the waves, and then the waves would sort of wash you about, right? And you would be tumbling about here and there, and you would be following a very zigzag sort of path actually. But this is very simplified, and we have shown the total distance as a sum of two displacements. All right, now let's move on. This is about displacement and distance. I'm sure you've got the basic idea. Now let's move on to motion in one dimension, in 1D. Motion in one dimension. One dimension. Okay, or 1D. I'm sure what one dimension signifies, right? It's just it's along a straight line, either backwards or forwards on that line. And we can call this line the x-axis, x and x dash, and we can arbitrarily choose an origin in here, right? An origin, or we call that O, and we consider it as the initial point of our journey. All right. So motion in one dimension. Now let's say, uh, let me change back to my color. Uh, this is story number 2. Let's say at this point, which I arbitrarily choose as O, the origin, I am in a car, a nice sedan. Doesn't look like a limo or anything, but just think that it's a limo. It's better if you imagine it to be a limo. You'll find it to be more entertaining. This is a limo, all right. And I am traveling in this limo, and I'm a very capricious sort of person, right? Very capricious, very fickle minded. And first, I asked the driver to take me, let's say, 100 meters forwards. I see a nice shop that I like with some maybe designer goods hanging in the window. And I ask him to take me there. And this is 100 meters. X is graduated in meters. Okay, in meters, this is 100 meters. Once I reach that shop, I realize that I don't need any of the goods in there, and it's kind of boring. I need to get back. Okay, so I get back in the car, and I ask the driver to take me back, and I see a really nice sort of really nice game studio back there, a really nice sort of cyber cafe, and I see that people in there are playing Counter Strike Go, or maybe GTA 5 in there, and I want to join them. Okay, and let's say I am going back by, this is 100 meters, right? Let's say I'm going back 150 meters. Now, what do you think? You've done graphs, right? What do you think should be the graduation for this? What do you think the numerical value of this displacement should be? Huh? It should be minus 50, right? Because if we consider O as our origin and we consider one direction, this direction to be positive, then automatically this direction becomes negative, right? So that's how it works. Okay, this is plus and this is minus. So accordingly, 100, this is minus 50 because it's 50 meters back, right? Now I'm tired of GTA 5. I'm tired of maybe Fortnite or whatever game it is I'm playing, and I tell the driver to drop me off at my home, which is 30 meters, 30 meters from the cyber cafe. Okay, from the gaming studio. I tell my driver to drop me off back there. So this is 30 meters, right? So what do you think this graduation should be? This graduation should be. What is 50 minus 30? 20, right? So minus 50 plus 30, it's in the plus direction, minus 50 plus 30, that's minus 20, right? Okay, so this is my final destination, and I get dropped off here, and I am very happy, but I'm not so happy because I'm capricious and I'll probably call the driver once again to get somewhere else, but that's a story for another day. I get dropped off here, right? So now this is in one dimension. We are going along this line either in this direction or in the opposite direction, right? So this is in one dimension. Okay, so let us talk about the distance and displacement in this case. Okay, distance. So distance, what do you remember from the definition? The definition is the sort of the foundation on which this entire lesson stands on. So what do you think about the distance? It's the total path length, right? So what is the total path length? First I move from O till 100. from O till 100, I move 100 meters to the designer shop, right? So first let me plug in the value 100. Okay, from O till the designer shop, O to designer, all right, shop. Okay, then I go back 150 meters, right? Now this does not have any directionality. As I told you, it's a distance, so it's a path length irrespective of whatever sign this number line, this x-axis is taking. It's just the path length, right? So I just add 150, and this is from designer shop, from the designer shop till the gaming studio, the game studio. All right, plus 150, and then finally I go another 30 meters from the game studio, to my home. All right, game studio to my home, and the home, my home, is the final destination. All right, my home is the final destination, and so I think we have plugged in all the necessary values, and we can proceed to calculation of the total distance I have traveled. So 100 plus 150, that's 250, plus 30, that's 280 meters. All right, the distance is 280 meters. All right, now let's talk about the displacement. All right, now let's talk about the displacement. Now displacement is the shortest path length between the initial and the final positions, right? The shortest path length. So that is the final position in one dimension, that translates to final position minus initial position. Final position minus initial position, and we signify that as x final, xf with a subscript, x with a subscript f, and xi. All right, so what do you think is the final position in this case? It's this one, right? It's minus 20. It's minus 20, right? So this is the final position, and O, or 0 meters, that's the initial position, right? So what do you think is the displacement in this case? It's very simple, right? It's minus 20 minus 0, and what's that equal? Equal to minus 20 meters. Now hold on a minute, distance and displacement, this is a straight line, right? So then why are distance and displacement different? I thought displacement was just the straight line distance, the shortest straight line distance between two positions, the final position and the initial position. Well, yes, but the key word in that is the shortest distance, all right? The distance per se is the entire length of the path that we have traversed, now whether it be back or forth or whatnot, I don't really care about that, but the displacement is the shortest path, right? And here you can see that this is the shortest path. I'm just going back over this path, and that's just it. Okay, so that is my displacement, right? The shortest path. So this is my displacement. It's that simple. Okay, this is my displacement. Okay, so I think you've got the hang of this story, and basically this is what this is all about, motion in one dimension, right? So I'm not sure what you were thinking when you saw the word kinematics. Oh my god, that's such a, it sounds like such a difficult word, what a difficult subject, right? But in reality it's that simple. The entirety of physics is this simple, all right? This is all there is to it, and the beauty of physics is that you don't need to remember much. You just need to apply whatever limited definitions you've learned. You need to apply it in the form of concepts, and you'll get everything correct. There's no two ways about it, all right? Okay, so now that we have got motion in one dimension, motion in a line, in a straight line, out of the way, let us talk a bit about an important part, which is, let me just take the screen completely down, which is position time graph. Position time graph. All right, position time graph is very important, and you should pay attention when I'm talking about this. Okay, and let me I think I'll make my screen smaller by a bit. Okay, and now let me tell you about story number 3. Story number 3. Before that, I'll draw the axes of my graph. I'm sure you all know how to draw a graph. I'll draw the axes of my graph. Let's say this is the y-axis. All right, the y-axis, and this is my x-axis. Now let's label the axes: y, y dash, o, x. Okay, now this part is the positive y-axis, this is the negative y-axis, and this is the x-axis. All right, and if I label the axes, the units on the axes, x is going to be time in seconds, and y is going to be position in meters. All right, and I wanted to think about why I haven't drawn the negative x-axis. All right, I've drawn the negative y-axis, that's fine, but why not the negative x-axis? That is because it's very simple, it's very intuitive. Time cannot go backwards. Time marches on, time always marches forward. There's never any looking back. You can think about the past, but you cannot go back to the past, right? So time always marches on, and that's why time is always positive. Time never goes back. All right, time is never negative. All right, okay. Now let's say this is you. Okay, this is you on top of the world, right? This is you, and you will be going for your evening jog. All right, an evening jog, it's very important to exercise at least a kilometer of day of jogging, or 5 kilometers a day of walking, brisk walking is very important. All right, so you are going for a jog, 1 kilometer. As let's say it's not 1 kilometer, let's say you are feeling lazy, a bit lethargic that day, and you just want to go maybe 200 meters. All right, let's say you're sprinting, not jogging. All right, 200 meters sprint. Okay, and this is you, and this is at time 0, at your initial time. All right, this is you, and your initial position is your home. Let's say this is your home, and the initial time t equal to 0, and at t equal to 0, at t equal to 0, let's say your home is at position 0. Arbitrarily I choose the coordinates for your home as 0 comma 0. All right, the first 0 stands for time, of course, because the x-axis is the time, and the second 0 stands for the position in meter, which is along the y-axis. All right, so at t equal to 0, you are at 0, and let me make that point right over here, and let me circle that point. All right, okay. Now let's say you're just about to go for your jog. All right, and then your mother intercepts you. Your mother intercepts you. Your mother intercepts you and gives you a list of items that she wants bought. All right, and you just wanted to go for your jog, and doesn't look great. Let's make another one. And you just wanted to go for your jog, and you don't like it, and that's why your hands are on your head. All right, and so you are still at your initial position, right? You're still at home. Ignore the little bit of difference that I made. It's just think, just consider that you are still at the same place when your mother intercepts you, and it takes 1 second for your mother to hand you the list, all right? And this is 1 comma 0. Why 0? Why is the y-axis 0? Because you're still at the same position, right? You're still at home, okay? And so 1 second has elapsed, 1 second has passed, and I draw a line to signify that 1 second has passed, but you're still at your initial position, all right? You're still at 0. Can you see the coordinates? This is 0 comma 0, this is 1 comma 0, all right? So 1 second has elapsed and you're still at your initial position. Now let's say you begin your jog, all right? You begin your jog, your sprint, I'm sorry, and you're sprinting, and let's say you are immensely fast, tremendously fast, all right? You're faster than Usain Bolt, you're faster than a cheetah, you're as fast as a bullet, all right? And let's say you are running 200 meters, 200 meters, this is 200 meters, and let's say you've completed it in 2 seconds. Wow, wow, that's just unbelievable speed, right? That's just unbelievable speed. You've completed 200 meters in 2 seconds. Okay, you've completed 200 meters in 2 seconds. So what do you think the coordinates should be, right? I'm sorry, I shouldn't have drawn that line, but let's just say, what do you think the coordinates should be, all right? This is t equal to 2 seconds? No, why not? Why do you think not? Huh? Why do you think not? Because you started running at 1 second, you ran for 2 seconds. So this is 2 plus 1, 3 seconds, all right? So what's the coordinates now? 3 comma 200. Why 200? Because you run 200 meters, right? So let's say this is around here 3 seconds, and that is 200, right? So I draw a straight line here, and I draw a straight line here, and let me make that a dotted line, this also a dotted line, okay? And now I have run straight for 200 meters, right? I just join the initial and final coordinates, that's it, okay? And this is my third point, which is 3 comma 200. Okay, now when after jogging, it's uh, after jogging you feel even more energized, and this isn't what kind of happens in reality, but let's just say this is a fictional world, a different universe where this happens. After jogging you are even more energized, and you can now run with twice the speed, say, okay, where you can run with twice the speed. Oh my god, now you can run with twice the speed, and you suddenly remember, why can you run with twice the speed? Because you had forgotten about your mother's assignment, and now you suddenly remember that you have to go to the shop, and you run in the wrong direction. Okay, there's no shop nearby, you have to go the opposite direction. So let's say the shop is also, let's say the shop is 100 meters in the opposite direction, 100 meters in the opposite direction, that will be around here, 100 meters, and this will be minus 100. Why will it be minus 100? Because your home is arbitrarily chosen as the 0 point, right? Your home is arbitrarily chosen as the 0 point, and so you've run 200 meters in one direction, in the plus y direction, which we've taken as positive, and now you're running 100 meters in the negative direction from your home. In total you're running 300 meters. That's what it basically signifies, isn't it? So you're running minus 100 meters from your home to the shop, and now let's say you run that in 2 more seconds, right? In 2 more seconds, and that's 5. Okay, so now let me draw a straight line from here, and I'll make that line dotted. You kind of get the drift, isn't it? And it's becoming pretty simple now, right? And I make another line like this, horizontally parallel to the x-axis, and I also make this line dotted. All right, now I join the initial and final points. Initial point is at 3, 200, and this final point is at 5 minus 100, right? This coordinate, of course, uh, this coordinate, it's 5. 5 is the x-axis, and minus 100. Okay, you kind of see where we are going with this, right? The y-axis denotes the positions where you are. I'm sorry, I haven't drawn you running back to the shop, right? Let's say this is the shop, and this is you running back at a multiple of the initial speed, right? Let's say like you're running so fast that you're running faster than the wind, all right? For fear of your mother, and let's say your hair is just flowing backwards like this, okay, and your feet are they are just stamping the ground, all right, and this is how you're running, okay, and this is t equal to 5 seconds, so 5 and minus 100, okay. You like the story, right? You see where this story is going, right? That's the main thing. I don't it's not important whether you like it or not, but it's a pretty lame story, but it's very important to see where this is going, okay. And now you have picked up all the items on the list and you breathe a sigh of relief, because if you had forgotten, god knows what would have happened. Maybe grounded for a week without access to TV or games or whatever. So now you breathe a sigh of relief that you can at least keep your hands on the controller or the TV remote for a sizable fraction of a week. And now you have to return home, okay. And to return home, you again run back home, because you figure, why not, let's do some more exercise, right? It's good. I like running this way. I'm running faster than Usain Bolt. If I sign up for the Olympics in 2024, perhaps I'll even get a gold medal, right? So you decide to pursue that, and you run back home, and let's say you run back home in 1 second. In 1 second you run back home, so that's the 6th second, right? And now, where what will your position be? Let's say this is your home. Let's say this is your home. All right, this is your home. It's got two nice fenestra windows and a nice hetish doorknob, and you reach back home. Now you are tired, and there's some droplets of sweat right around there, and now you're tired and you've reached home, okay. And this is in the 6th second, t equal to 6 second, okay. And what will the coordinates be now? What will the coordinates be now? The x-axis, of course, will be 6. And what about the y-axis? You've returned home, right? So you were back to where you were initially. You're back to where you were initially. Kind of pointless, right? You're back to where you were initially. So how much, like, where have you gone? What's your position now? It's back to 0. My god, all this work has been for nothing. I've been running so fast, faster than Usain Bolt, faster than a cheetah, faster than a bullet. And where am I back? And where am I? Back to 0. That's kind of disappointing, but that's how it works, okay? That's how physics works. That's not how physics works. Physics isn't disappointing, but yeah, that's kind of how this whole arrangement works, alright? And I draw, this is my final position is 0, and it's at 6 seconds. The line isn't all that great. Here, alright? You're back home, back to position 0, and the time is 6 seconds. 6 comma 0, okay. So I think that gives you a pretty good idea of how a position time graph works, right? You've got the position on the y-axis and time on the x-axis. That's kind of what any book will tell you: position on y-axis, time on x-axis, and this is how the position changes with respect to time, and blah blah blah. And it's all very drab and boring kind of stuff, but you just if you have paid attention to this really lame story, I think you've got a pretty good idea of how things work, right? And I think now we can move on to a problem. Let's say this is a question, and let's say I draw a position time graph right here, y-axis and the x-axis, all right. And let's say the graph looks something like this. All right, it can look like that. As you've seen above, position can be both positive and negative. Time is always positive, so let's say it looks like this. All right, and let's say this is at minus 20 meters. Minus 20. I don't have to write meters because I'm going to be labeling my y-axis in meters. Y dash x, and this is going to be in meters, and this is going to be in seconds. All right, and let's say, let me take the dark blue in case of this one, dark blue, and dotted line, and let's say this is 1 second, 1 second, 2 seconds, 5 seconds, and 6 seconds. All right, and this is 0, right? O, and this distance, this position on the y-axis, let's say this is 100 meters. It's not exactly to scale, but that doesn't matter. What matters is your understanding of it. So let's see the question. What is the question? Find displacement and distance from 0 to 6 seconds of travel. All right. So how do we approach this? It's a really simple question, and there's a very easy way to approach this. Let's find out displacement x. Okay, displacement x equal to, now what is displacement x? It's x final minus x initial, right? Final position minus initial position, shortest length of the path between the final and the initial position. Ring a bell? I told you about it a few minutes back, about 20 minutes back. So this is x final minus x initial, right? So what is the initial position? X initial equal to, you see it's minus 20, right? This right here, this is where we were at time t equal to 0, right? So x initial is minus 20, and what is the final position? Let's just kind of, you know, toughen it up a bit. Let's do something. Let's, instead of from 0 to 6 seconds, let's make it from 0 to 5 seconds. So what is the final position? Now you may be tempted to say it's 0 because it's 0 at 6 seconds, but we are talking about 5 seconds, right? So this is a position we are talking about, right? So this has to be the x final. All right, that has to be the x final, and this is the x initial. So what is the x final? X final equal to 100 meters. 100 meters, it's all in meters. X final is 100 meters. So what is displacement x? X final minus x initial, 100 minus minus of 20, which equals 120 meters. Wow, it's really simple, right? It's really simple, and you kind of don't need to think about it at all, right? It's all you just get it right from the graph. If you were to say make a position and time table sort of thing, and then you had to plug in the values and to make the necessary calculation, that would have taken a much longer time, right? But a graph, it's very elegant, it's very it saves a lot of your time, and it's better in all respects, right? You get to visualize it right in front of your eyes, and you get to you kind of get to see the paths the body is following, right? So that's why we prefer graphs over tables or statement type numericals and all other ways of solving problems. All right, so I have found out the displacement, and now let's say distance is denoted by s. Okay, distance s is the, what do you think? What was the definition? Total path length. all right, total path length. Okay, so I want to find the distance from 0 to 5 seconds. I want to find the distance from 0 to 5 seconds, and what I need to do is to calculate. Let's say, let's not find the distance from 0 to 5 seconds. Let's say displacement is from 0 to 5 seconds, and distance is, as earlier, from 0 to 6 seconds. This way it will be more fun, right? You'll get what I mean in a minute. Okay, so let's calculate the total path length. So initially, what does it do? This is how it moves, right? This is how it moves. It moves from it. Let's calculate from x initial to, let's say, this point is xa. Let's call it xa. All right, to xa, which is, how much do you think this is? It's 100 minus minus 20. Xa minus xi, 100 minus minus 20. That's 120 meters in itself. 120 meters in itself. Next, what do you think it does? Is it moving in this case? Well, no, right? It seems like it is moving from 2 to 5 or whatever, but remember, 2 to 5 is the time. It's not its position, right? It's staying at 100. So let's name this position as xb in this case, all right? Xb. So from xa to xb, from xa to xb, what do you think it is? 0? Because it's not moving, right? It's staying at 100 meters from whatever the reference point was. So it's 0. Okay? And finally, it's moving from here to this point. This point is xf. That point is xf. So from xb to xf, how much do you think this is? The final is 0, right? And the initial is 100. So that's 100 meters. 100 minus 0 is simple, right? It's 100 meters. 100 meters. Alright. So what do you think the total path length is? It's just a sum of these, right? That's simple. 120 plus 0 plus 100, and that is equal to 220 meters. Wow, that's so simple. That's so simple, isn't it? Where's my square working? Let's just see. That's so simple, right? And I'll put a rectangle around my displacement as well. So the displacement in 5 seconds is 120 meters, and the distance in 6 seconds is 220 meters. And now, I think you see why I didn't take the distance from 0 to 5, right? Because then it would have been the same as the displacement. It would have been 120 meters, since it just stops from 2 to 5 seconds, right? So that's why that would be kind of boring. That would kind of defeat the purpose of this entire exercise, right? And let's just take the displacement from 0 to 6 seconds as well and see what that kind of is. So now this time xf is at 6 seconds. It's 0, right? Because you see the graph, it's at 0. You've returned to your original position, and initial position is at minus 20. So 0 minus minus 20, that's 20 meters. Okay, so it's very simple. You could have done this by yourself, right? 0 minus minus 20, that's 20. So the displacement in from 0 to 6 seconds is 20 meters. Okay, and I think this should be enough for the purpose of delving into the basics of kinematics. I hope you liked this video, and I hope you understood all that I had to all that I had to say. And if you just take things simply, okay, this is very simple, it's very easy, and it's very rewarding when you get a question correct. All right, so thank you. Okay, bye, see you later.